Going over the quiz on thermal parameters. Okay, so let me look at it and we will solve all the questions. So first, question 1. The thermal resistance depends on the thermal conductivity of the material. Well, that's true. There's nothing to say about this. It depends, the thermal resistance depends on the thermal conductivity, and it depends on the thickness or the width of the material, but it depends on thermal conductivity. Second, the thermal transmittance is used to calculate the thermal loads through the building envelope. Yes, so we use thermal transmittance, is the U value, so that's true. Question 3. So this is, here you have to type can you hear me, by the way?
Yes.
Yep, we can hear you.
Okay. Rebecca, what's wrong? Or Scott, you can't hear? Okay, you fixed it? Yeah, probably there's something wrong with your computer. If you can't hear me, it's because you have muted your speakers or whatever, because my system is working. Okay, I'll continue. Then here you are supposed to type a number. So if the thermal conductivity of a material is 5 BTU inches hour Fahrenheit feet square, and the thickness of the material is 5 inches, the thermal resistance is, well, that's very straightforward because this is the thickness 5 divided by 5. So here you should type 1. And that's, I think this is the question. Some of you might have, yeah, and that was my mistake, because that, the thermal resistance, I think I should have added here the units, but I added only the value itself. But next time I will add the units, okay? So, but here you have to just divide 5 by 5, so it's 1. Question 4. Passive house standards for construction are is mandatory all over the United States. Well, this is false. It's not mandatory. It's recommended, especially in the Northeast, where in cold, I think not in the Northeast, in cold areas of the United States, this is the recommended standard. But it's not mandatory. Okay, so there are things that are mandatory, there are things that are recommended. And but we have to make our decisions. So there are federal laws, the things that are mandatory all over the United States. Then there are state laws, things that apply only to the state we are living in. And then there are things that are mandatory. They are not mandatory. They are recommended good practices of construction. And the passive house standards, it's one of the recommended things. If I had to make a guess, I would say that in 10 years, that would be mandatory in cold areas of the States. I think passive house doesn't make any sense in Florida or in South California, so there should be other standards for those areas. But in cold areas, in north or northeast or northwest areas of the country, or I think it makes sense. Okay, but so I think that at least in the Northeast, because there's a very strong community of architects that are committed to passive house standards in the Northeast of the United States, in New England. So if I had to make a guess, I would say that in 10 years it would be mandatory, but I don't know. Then the most efficient windows are, here we have triple glazing. Single glazing is not. Double glazing, if we have double glazing, is not the most efficient one. So if we have triple glazing and triple glazing with low emissivity coating, this is the right answer. What about, what's the difference between, or what is the best one or the most efficient one between the triple glazing and double glazing with low emissivity coating? Well, I don't know. I need more information, but with this information, this is the most efficient one. Triple glazing, it's always better than double. And low E coating, it's better than not having a low E coating, low emissivity coating. Then question 6, the recommended thermal resistance for walls in New Hampshire, according to Passive House standards, is, it's always 50, but then we need the units, okay? So the units for thermal resistance, it's this one. It's 50 hours feet square Fahrenheit divided by BTU. Okay, so 50 is not enough. It's not the correct answer. And then which thermal insulation has the best thermal conductivity? When we're talking about the best thermal conductivity, we're talking about the lowest thermal conductivity. So in terms of thermal conductivity, extruded polystyrene is the best because it has the lowest thermal conductivity. Then there are other aspects like the life cycle, the CO2 emissions, and there might be other options. But if we only look at the thermal conductivity, extruded polystyrene is the best one. Then what is the thermal envelope of a building? So here we have different definitions. Is it the area of a building between the basement and the attic? No. No, it's not correct. It might be. So if you look at this, yeah. So sometimes it is the area of the building between the basement and the attic. If we don't have thermal insulation in the basement and we don't have thermal insulation in the attic. But if we do have thermal insulation either in the basement or the attic, this is not correct. Is it the floor area of the building? No, it's not. And here we have two, yeah, so is it the union of those structures that separate the conditioned part of the building being heated or cooled from the outside? Yes. And this is the same, but from the neighbors. No, for example, in residential buildings, not in single family houses, but in apartment buildings, the thermal envelope is not the element that separates us from the neighbor, because neighbor, if we have different flats in the same building, the thermal envelope has to do with the outside, not with the neighbor itself, because the neighbor, if he's using the heating system, the neighbor's temperature would be the same as my temperature. So there is no heat transmission through that wall. Okay, so the thermal envelope is always referring to the separation between indoors and outdoors. So that's correct. So if I submit this, correct? Yes, yes, yeah, okay. Everything's correct. Okay. So make sure that you submit all those quizzes. It's very straightforward, and I think if you make the wrong choice, you have feedback with the correct answer. So I want just to, it's just another way to take the attendance. You have to attend the lesson, and at the same time, you have to complete the assignment, the quiz, sorry. Okay, so Cyrus, are you there?
Yeah, I'm here.
Okay, let me. Okay, so let's go over today's lesson. So today we're going to talk about heating loads, or yeah, so finally we're going to calculate this. We're going to calculate the heating load, which is the U value, the area of the element, can be a wall, a roof, floor, windows, whatever, and then indoor minus outdoor temperature. Today we are going to look at floors, because floors are special, and we can have either basement or a crawl space, or none of the, or neither of them. Okay, so we can, there are different options for floors. So let's start studying the options. In single family houses, I think 90% of single family houses in the United States, they have either basement or a crawl space. So basements are different because Basement is it's like another room. Usually we have basements with storage or mechanical rooms, so it's not a conditioned space. It's not something that has heating or cooling systems. But it's a place where people can stay. A crawl space, it's a very low space, so people cannot stand here because it's like 2-3 feet. Okay, so we can't stand on a crawl space. And why do we need this? Okay, so there are different functions. So first, that crawl space provides us with protection from the ground, from the soil. Okay, so here in that soil, we have a lot of things. We can have a rock soil, and this is not, well, this is the best one, but even in rock soils, we have, let's say, moisture. For sure, there will be moisture if it rains. The rain is filtered through the soil. We have animals, we have bugs, we have plants. Okay, so there might be a lot of things in the soil, and just this is something that human beings have done throughout history. So they have protected from nature, because nature, it's great, and we make the most of nature. We make the most of water. We make the most of sun, wind. Everything's nature, but nature has its dangers. Okay, so especially if we have moisture, animals, plants, insects, worms, I don't know. There are a lot of threats to our house, and we need to protect our house from those threats. So one a different, I mean, a very cheap way to protect houses from the threats that we have here in the soil, it's to elevate the house just 2 or 3 feet. Okay, so usually when we want to enter the house, we always have some stairs, let's say 2-3 steps, and that's enough. Okay, so just be above the grade level, yeah, like 2-3 feet. It's enough. On the other hand, if we protect this and we do not ventilate that crawl space, there might be terrible things happening here. What kind of terrible things? Okay, if we don't ventilate, there might be beings growing here. So we might have some species or animals or plants or things that we don't want in our house. And if we don't ventilate and clean up that space often, probably there would be things here that are scary. Probably if you are not aware of that, but if you haven't checked your crawl space for, let's say, 10-15 years, there might be something scary living here, and that's fine. But well, that's fine. I don't know. As long as we are not aware of that, it's fine. But anyway, we have to ventilate that space, and from time to time, every, I don't know, 2, 3, 5 years, we have to go down and get rid of things that we don't want. There are companies doing this, and sometimes we have to spend some money doing that. Okay, but this is maintenance, and well, roofs need maintenance because if some tiles are broken or the wind has removed tiles or shingles, there might be water leaks. So we need maintenance in the crawl space as well. So that's it. But we are analyzing this from the thermal point of view. So we're analyzing heat losses here. Okay, so we have to understand all these. If this is the indoor space, so the indoor space is it's a comfort temperature, 70 Fahrenheit. Outdoors, if it's winter, it's cold, so we can have 20 Fahrenheit. We have this crawl space. Okay, so this crawl space, we have different temperatures here. So this is the outdoor and indoor temperature. So that's easy to understand. But the crawl space, it's something that doesn't have a heating system, because we don't have a heating system in this space. It doesn't make any sense. And it's ventilated. So that means that the temperature here is it's not going to be a comfort temperature. It's not going to be 70 Fahrenheit, sorry. But it's not 20 Fahrenheit either. So it's something in the middle between 20 and 70. So it can be closer to 20, it can be 30, 35, or it can be closer to 70. It can be 50, 55, 60. So it depends on many things. It depends on the amount of ventilation that we have here. It depends on if we have thermal insulation in that floor or we don't have thermal insulation in that floor. But the temperature is different. So I typed here 50 because we have to understand that this is something between 20 and 30. And then we have the soil temperature. So the soil temperature is not 70, it's not 20, it's not 50, it's something different. So the soil temperature usually is above the outdoor air temperature. So if the outdoor air temperature is 20, the soil temperature should be slightly above, but it's not comfort temperature as well. And so usually we have this. This can be 20, this can be slightly above, then we have the crawl space temperature, and finally we have the comfort indoor temperature. So if we want to solve this problem, we have this equation. This equation is quite complicated because it depends on the amount of ventilation that we have here in this crawl space. It depends on the U value of all the materials. We have the U value of the floor itself. We have the U value of this wall, the crawl space wall. We have the U value of the soil itself, and then it depends on the temperatures. It depends on the outdoor temperature and the indoor temperature. We can measure those temperatures easily, but do we measure the crawl space temperature? Yeah, we can have a thermometer there, but usually we don't have it. And do we measure the soil temperature? We can, but what's the point? We don't know. Okay. So if we want to accurately decide the heating loads or the heat losses through this floor, we need to take all these things into account. All these temperatures, the U values of that wall, the U value of the soil. So there are a lot of parameters that we need to understand. Is it worth it? Well, I don't think so, but this is it's my opinion. I'm going to make some assumptions, and I'm going to make those assumptions from the safe side. Okay, so we're always making assumptions in our life, and as architects, we're always making assumptions. They're not. So what is the outdoor temperature? So we're not constantly measuring the outdoor temperature. Oh, now it's 20. Oh, no, it's 21. Oh, it's 25 now. Okay, so we say, let's say 20. And why do we say 20? Because probably it's the lowest temperature that we can find in this place. Okay, so now we have to go over climate data. And the minimum temperature that we have had in New Hampshire, it was, well, it's not 20, it might be below 0. But I can use this to be on the safe side. Okay, so if I use the minimum temperature in history of Keene or in the history of New Hampshire, I know that most likely temperatures won't be below that value. So the heating system I'm designing, it will work 99.9% of times. Okay, so I'm on the safe side. If I use, let's say 30 Fahrenheit in Keene, New Hampshire, well, we do know that sometimes the outdoor temperature is below 30, it's below 20, and it's even below 0. So if I use 30 Fahrenheit for my calculations in Keene, well, we know that our client, maybe 10% of the time or 10% of winter time, he won't be able to heat up, or they won't be able, the clients won't be able to heat up their houses. That's a problem. So that's why if we want to be on the safe side, we better, okay, so what is the minimum temperature? Okay, so I will make all my calculations with the minimum temperature. So with this, if I want to be accurate, I have to solve this equation. It's quite complicated, so I wouldn't do that. So I have two options here. So I need to provide this here. We don't have any thermal insulation in the floor. But here, we can either place thermal insulation here, and this is the thermal envelope you remember that we worked, or we explained what the thermal envelope was here. Okay, so in this case, if this place has a temperature of 40 Fahrenheit, that means that it's not a living room, so people are not living here. So the thermal envelope is this, and I have to place my thermal insulation where the thermal envelope is. Okay, so in this example here, the thermal envelope is here. I have thermal insulation in the wall, and I have thermal insulation here in this floor. And then I assume that the crawl space has the same temperature as we have outdoors. Okay, so the temperature of this crawl space is the same as the outdoor temperature, is 20 Fahrenheit. Maybe this is not true. Maybe the temperature here is not 20, it can be 30, 35, 40. So we are overestimating the heat loss, because the heat loss here, or the thermal loads, it's the U value of this floor times the area of the floor times indoor minus outdoor temperature, 70 minus 20. Okay, so I know that it's going to be less. It's not going to be 20 minus 70 minus 20. Probably it's going to be 70 minus 40 or 35. But I'm on the safe side. So I know that my client won't have any trouble heating up that space, because I have overestimated the heat losses. Okay, so that's fine. If I want to be accurate, and if I don't want to overestimate anything, let's do this. Let's solve this question. But if I make that assumption, and if I know, okay, so the thermal loads most likely will be lower than my calculations. So my clients will be comfortable there, because I overestimated the thermal loads. Okay, we can either do this. This is what I recommend. So I recommend you use thermal insulation here inside the house, because look at this here. We have a continuous thermal insulation, and this is always good. Okay, so if we have a continuous thermal insulation, it's always good. We can do this. So we can continue the thermal insulation, and we can have the thermal insulation on the walls of the crawl space, and here on that where the soil is. Does it make any sense? Well, I don't know, maybe. I wouldn't do that. But if there are others that, okay, if you find other architects or other building scientists that recommend you do this, okay, listen to them, let them explain their reasons, and then you can make your own decision. If I had to build my own house, I would do this, okay? But there might be, especially if we are dealing with ventilation loads, there might be some, yeah, so it might make sense. But in this case, what I am assuming is that the temperature of this crawl space, it would be around 70 Fahrenheit, because I don't have any thermal insulation here. So if I'm heating up that space, the indoor space, I can end up heating up the crawl space as well. Does it make sense? I don't think so. But, well, there might be some times in which, yeah, it can be reasonable. Anyway, this is my recommendation, but it doesn't mean that this is the truth and nothing but the truth. No, there might be other options, other solutions. So listen to other solutions or other opinions. And if it's reasonable, okay, you can accept them. If it's not reasonable, go ahead with your own opinion. It's not your opinion, it's your own criteria. So we're going to do this because, well, I'm teaching that this course. So I will use this option that I think it's a good one. If it's not the best, I think it's good enough. So that simplifies things a lot, because if I want to quantify the thermal losses here, I need to calculate the U value of the floor. We know how to do that. I need to measure the floor area. It's very easy. And then I only need to know the indoor minus outdoor temperature. So I don't need to calculate that crawl space. With this equation, I need to calculate the crawl space, and I need to know the ground or the soil temperature. It's more complicated. Probably it's more accurate, but it's more complicated. And I think this assumption, it's good enough because we are on the safe side, because we are overestimating the heating loads. Okay, so now we have to analyze details. So if you remember, there was a book I recommend you, or one of the recommended books in this course. It's the Builder's Guide to Cold Climates. So this detail is taken from that book. So this is the book. Okay, and if you leave over that book, you will find that there are a lot of details, like this one, okay, with crawl space. And it's very useful because here we are analyzing only materials from the thermal point of view. But in this book, you will find that there are other aspects of building construction that we are not analyzing in this course, like waterproof layers, or how we deal with moisture. Okay, so we will learn this in other courses, especially in building science too. But in this course, we're only dealing with thermal transmittance, thermal resistance, thermal conductivity, the thermal aspects of those buildings. But I think it's good going over those details, because there are a lot of details here, and if you find those details in that book, that means that they are good details that you can use. You can copy and you can use. Okay. So I think it's good having this building, because there are things. Look at this detail. Okay, so there are a lot of information here. This is the crawl space. This is the ventilation at top of the foundation wall. This is a concrete foundation wall. This is something, usually we have these concrete walls here in those crawl spaces or basements, because we have to prevent the soil from contacting the wood structure. Okay, so it's always good having this to protect the wood structure from the soil, because in the soil we have insects. So there are a lot of insects that eat wood. So if we bury our wooden structure in the soil, that's risky. I wouldn't do that. So that's why having concrete, if we have a basement, for sure it has to be concrete. But even if it's not a basement, and if it's only the crawl space, I would use at least concrete masonry units. You can use brick, but concrete is more reliable than brick. So what do we have here? We have a lot of things in that detail. So first we have this concrete wall. This is the footing. Okay, so because we have that concrete wall, and then you need a footing made of concrete as well. If you take structural or statics next year, you are sophomores, but in the junior fall semester, you can take introduction to structures or statics, and you will understand why we need retaining walls, footings, and all that stuff. But, well, look at this. First, we need ventilation. Okay, so we need to ventilate that crawl space. Then look at this. We have a drainage, a crawl space drain. Why? Because that crawl space, we can have moisture, and that moisture can condensate, and we can end up having water, actual water, liquid. And we have to get rid of this. Okay, so it's always good having like a drain. As you can see, we have slope. So at the end of this slope, we have a drain, and we can get rid of water. That's good. Here we have another drain. Okay, because if it rains here outside, the water, the rainwater can filter. And before contacting this concrete wall, we need to get rid of that water. So the rainwater will filter here, and here we have this pipe, and this pipe will get all this water, and then it will get rid of it. Okay, and that rain, this element here, is around the house. It's not just here on this elevation, it's just around the house. So that's a good practice. So basically, the history of architecture is the history of protecting human beings from water. Water is the enemy in buildings. Okay, so if it rains, we have a roof and we have a tilted roof and we get rid of water. So that's easy. But then the water will fall on the ground and that will filter. And if the water filters and if we don't have something protected against water, it will end up entering the crawl space. And if we have a lot of water, a lot of moisture in this crawl space, we will end up having that water indoors. Okay, so we need to protect this. So this is a protection against water. If we have some water in the crawl space, then we have another drain. So that's another protection against that water. And finally, if everything goes wrong, or if it rains a lot and we have a flood here, imagine that the water level rises up to here and we have water inside the crawl space. So here we have another protection, and this is a foil-faced polyisocyanurate. Okay, so that material, it's important because we haven't talked about that material, because walls, well, in walls we don't have issues with water. We have to be very bad architects to have issues with water in walls, okay? Especially water leaks. We can have issues about condensation. We will talk about that. But water leaks in walls has to be something very wrong. We can have leaks in roofs, but we have the shingles. Okay, so by having shingles and having a good maintenance of roofs and shingles, okay, we shouldn't have issues with water in roofs. But here, this material, this polyisocyanurate, or something like that, okay, this is a waterproof material. This is a thermal insulating waterproof material. So if we Google this, okay, this is the polyisocyanurate insulation. Well, it's foam. It's a rigid foam board insulation, and well, it's something that can cope with water. Okay, so it's something that even if it doesn't get wet inside because it has a closed cell rigid foam. I don't know if you have studied chemistry. If you haven't, it's something amazing. But this closed cell foam or polymer means that we have cells like this. So we have atoms of materials creating those closed cells. And if it's closed, that means that a molecule of water cannot enter inside this closed cell. Okay, so the material itself is protected against water. If we have an open cell material, that means that water can flow through that material and water can go through that material, so it doesn't protect the house against water. Okay, so when we are using, when we want to protect something against water, we can use this foam, and foam is better than fiberglass or fiberboard. Those are not closed cell materials. So if we really want to protect things against water, we have to use this foam. But we can have an open cell foam or a closed cell foam. So we can use that, and that's it. So in that detail, no. Okay, in that detail, here we have this board that it's waterproofing. And it's a good thing because we can have moisture. We don't control what's underneath our house in this crawl space. So having this, it's good. And what else? Well, but look at this. There are a lot of things. And here, that with that book, you will learn not only things we are studying now. We're studying the thermal properties of materials, because this drain doesn't have to do with thermal properties of materials. This is to get rid of water. Yeah, we have to do that, but this is not building science. This is construction. Okay, so with that book, you can learn building science, and you can learn good construction solutions or details. Okay, so let's look at these two details. Here we have the crawl space, and here we have a floor without the crawl space. Is it acceptable? You might find people that, yeah, they think that this is a good solution. And I wouldn't do that. Well, I wouldn't do that. I wouldn't do that in living spaces. Okay, if we have a house with a living room and a bedroom, or we have a commercial shop, or we have a theater, or we have other commercial buildings, I wouldn't do this where people can stand. I can do that, for example, in carports. So in carports, I don't need a crawl space. Well, because there will be a car here, there won't be people, so we don't need comfort conditions where the car is, or a storage room, or a mechanical room. Okay, so if I have rooms where people are not living, I would go for this solution because it's cheaper. And if we protect, we have a waterproof layer here. So if we protect this, we won't have issues with water. Here we have aggregates. Okay, so this is a concrete slab, and here we have aggregates. So aggregates have a function. We will explain that in another class, maybe not today. But this is a good detail with aggregates, a waterproof layer, and then a concrete slab. It can work, but I wouldn't use this in rooms where people are spending a lot of time. I can use this in mechanical rooms, storage rooms, carports, garage. Okay, where if we don't have people living there, this is a good solution because it's cheap. It's cheaper. It's cheaper because here we need a structure, and yeah, we need to bear those loads here because this is empty. This is air. Okay. Anyway, either this or that, you can find both details. I recommend you this if you are going to work with houses. If you are working with basements, well, it's like this, but it will be higher. Okay, so a basement is not a crawl space. A crawl space is a 24-inch, yeah, 2-3 feet. If we are talking about a basement, it would be a 6, 7, or 8 foot space. But it would be the same. We would have a wall, a concrete wall. If we have a basement, most likely we will have something like that. We'll have the aggregates and another concrete slab here. So here we have directly the soil. We don't have another concrete slab there. Okay, so I recommend you this detail. And then if we analyze the materials and thicknesses and different layers that we have in this in a floor, okay, this can be something good. So in this kind of construction, there will be rafters and there will be thermal insulation in the middle. The same thing we saw last Monday on roofs. Okay, in the roof we have rafters; those are the structural elements, and then we can have thermal insulation here. Okay, so in the floor, we will have the same structure. There will be rafters, 2x4 or 2x6. The distance between rafters would be 16 inches. The width of this rafter would be 2, and that would be 14 between two faces of two different rafters. Okay, so those dimensions are standards. But the difference is that here, this is outdoors in floors. By the way, this is outdoors. So we have to use this polyisocyanurate board, let's say 3/4 of an inch, because we need to protect this from moisture and water. So this is not a OSB. This is not an OSB board or a plywood. It has to be this polyisocyanurate because it needs to be waterproof. Then we have either rafters or thermal insulation. We can have, let's say, fiberglass here. And then we can have a wood board. Let's say that this is OSB. And 1 inch is too much. Let's say half inch. Okay, and this is something new. This concrete autoclaved aerated, a 2-inch layer here. This is concrete. This is light concrete. This is not structural or heavy or reinforced concrete. So this is aerated. So that means that it's light. It's light, but it before the flooring. So this is the hardwood flooring. So before the flooring, we have this. And why? Well, I like this solution because if you have a structure like this one with rafters and boards, when you step on it, you will hear this crack. So when you are stepping on your, so you will hear this sound, and well, I don't like it. So if you pour this cast in place concrete, a couple of inches, it's enough. It will be more solid. Okay, so you will step on that floor and it won't crack or it won't make any noise. So I think this is comfort. Even we are not going to talk about the acoustics here, but listening to what your neighbor is doing upstairs or whatever, it's not pleasant. Okay, so by having this kind of heavy material, we can protect. It's more solid. So I recommend you use this light concrete. 2 inches would be enough. So if you are not using a solid concrete structure, and in single-family houses, we don't have this kind of structures, at least having this 2-inch concrete layer, it's good. And finally, we have the hardwood flooring. Last Monday, we spoke about the difference between hardwood and softwood. Usually when we're using structures, we're using softwood. 90% of times, pine, okay? Pine is softwood, and this is the structural wood that we usually design or use for these kind of structures. But hardwood, it's something that we're in contact with. This is what we see. And hardwood can be like oak or cherry tree, or, well, there are different materials for the flooring, and it has to be something beautiful. And usually the pine is not beautiful. Well, it's not beautiful. There are other woods that are more beautiful. And usually those hardwoods is the kind of wood that we use for flooring. It can be 1 inch or more. We can have rafters, and then we can have an air cavity. I don't know, there are different things. From the thermal point of view, it's not relevant, but we can have, we can have also ceramic tiles or stone, marble, whatever. But we need a flooring. It can be either wood, ceramic, stone, and that's it. So those are the kind of materials that we use for the flooring. From the thermal point of view, it's not relevant, but from the aesthetics point of view, it is. So probably your clients would say, no, I want a wood floor. Okay, what kind of wood? Something very expensive, because I'm going to brag about my house. So when my neighbors come over, I want them to say, oh, what a wonderful floor. Okay, probably. Or no, I want marble. I want travertine or I want marmol di Carrara from Italy. Okay, it depends. Okay, but from the thermal point of view, I don't mind. This is aesthetics, and of course there are better materials and worse materials, high quality, low quality. Usually the high quality materials are more expensive than low quality ones. But this is something that you have to talk to your clients, and they would see. From the thermal point of view, it doesn't make any difference. Okay, so now we are going to calculate this. You remember that when we were designing roofs, here we needed an extra layer of thermal insulation because we need an R value of 50 or more than 50. It has to be above 60 for in roofs. In floor, it's not in the floor, it's not relevant. So here we have, with this thermal insulating layer between rafters, that would be enough. And even this, this is thermal insulation, that this is too thin, so it doesn't have a lot of thermal resistance. This is more for protecting the floor or the wood structure against water, but it makes, yeah, so it's thermal insulating material, 3/4 of an inch. Okay, that's fine. But we don't need an extra layer of thermal insulation. These 4 or 6 inches, if we have these 4 or 6 inches between rafters, in floors, it's enough. But we do have 2 different sections. We have a section through the rafter, and we have another section through the thermal insulating. In this case, it's fiberglass. So we are going to calculate this. I will place this here, and I'm going to open the Excel file. There we go. Here and there. And this is the roof. This is the floor. Okay. So I'm going to delete this. Well, the most important thing is that you have already worked with this Excel file, and you have to, yeah, we'll keep on using this file to carry out the final energy analysis of a building. Okay, so what we are going to do now, I'm going to copy section 1 and section 2. So I select this, I copy, then I paste it. And this is not a roof, this is a floor. Section 1 through the rafters, okay? And then there's another floor here. Section 2 through the fiberglass. Okay, so now we have to change materials. So the first thing, if we are analyzing floors, we have to be careful because this is inside and this is outside. Okay, so in these tables, we have placed the exterior at the top of the table. This is good for roofs because in roofs, this is what happens. But in floors, I would do the other way around. So this is ext and this is in. Okay, because here we are inside and we go down and we are outside. So I think this is clear. Does it matter? I mean, does the order of materials matter when it comes to the thermal resistance or thermal transmittance? I don't think so, but not from the thermal point of view, but from the construction point of view, it matters, the order of materials. So, because we need the waterproof, in this case, we need the waterproof underneath the structural elements. In roofs, is the other way around. We need the waterproof element above the structural element. Okay, so get used to doing this so we can have exterior at the top of the table for roofs and interior at the top of the table for floors. I think it's easier to remember. But now we have to type different materials here. So the first material is the hardwood. Hardwood. Okay, and we can type the width now, it's 1 inch. The second material is this concrete autoclaved aerated. Okay, so this is concrete aerated. Concrete. Then the next material is the OSB board. Okay, so it's the OSB board, and it's a ½ inch. By the way, the concrete is 2 inches. Okay, so we have 1 inch hardwood. This concrete, yeah, it's 2 inches here. Then we have the OSB, ½ inch, OSB, ½ inch. And then we have a rafter, and the rafter is 4 inches. So it's the same thing we had for the roof. And here, but now we don't have another OSB. So this is the polyiso, whatever. Yeah. And this is 3 quarters. So the thickness is 0.75. It's 3 quarters. Okay, so we have materials, and then we have the width. Now we have to look at the thermal conductivity. Okay, so let's, we have to open lesson 3 again. That one. Okay, so we have these tables. So on lesson 3, we have to find the materials we're working with now. So the first material is the hardwood. Here we have the softwood, I think in flooring. Yeah, so here we have flooring materials, and we have a hardwood flooring. Okay, so the hardwood, the thermal conductivity is 1.1. So I can open again the there you go. Okay, so the hardwood thermal conductivity is 1.1. I'm going to delete this because I think it's confusing. Okay, so hardwood, an inch, 1.1 thermal conductivity. Then the concrete, aerated, whatever. So we have 2 inches. Do we have that material? We should, yeah. So you see that this is the concrete autoclaved aerated. So this is 0.26. We do have a thermal conductivity here. So this is 0.26. The next one is the OSB board. I think it's here. Yeah, so this is the OSB, and the thermal conductivity is 0.8. So this is 0.8. Then we have the rafter. The rafter is softwood, and we do have the thermal conductivity here, is again 0.8. 0.8. And this is the polyiso, whatever. And I think this is a thermal insulating material, so it should be here. Yeah. So this is the polyisocyanurate. And well, as you can see here, we have 3/4 of an inch. Okay, so the thickness here is 3/4. So we have to just go to the thermal resistance column, and the thermal resistance is 5.4. Okay, so we don't have thermal conductivity here, but we know that thermal resistance is 5.4. Okay, are we done? Not yet, because look at this. Now we have the thermal resistance of this indoor air layer and the thermal resistance of the outdoor air layer. But this has changed as well. So on this same lesson 3, I have to go to a different slide because we need different coefficients here. So that was the coefficient for walls, that was the coefficient for the roof, and now this one is the coefficient for the floor. So the floor means that we're going down with the heat flux, or the heat flow is going down. So that means that this is a floor. HE, it's 2.93. It's always the same. It's always 2.93. But HI is 1.05. Okay, so here I have to type 1.05, and here 1.05. Okay, so now this is the indoor air layer. So if I type this, there's a mistake because now it's outdoors. Okay, so I have to select this, and now it's this cell. It's 1 over HI, this one. And that one would be equals 1 over HE. There you go. And what about this? The thermal resistance, it's always the width, this one, over the thermal conductivity, that one. I click OK. And then I drag this down, 1, 2, 3, 4 cells, and I have all these values, all these thermal resistance. The total is the sum of all these values, 20, and the U value, it's this 0.0478. Okay, so this is section 1 through the rafters. Now I need section 2 through the thermal insulation. I have the same material, so I can select all these cells. You see, I can copy, and then I click here, and I can paste. And this is 1 over HI. This one is 1 over HE. This is not a rafter. This is the fiberglass. And what is the thermal resistance of fiberglass? I have to find out. So this is fiberglass 1 inch. Is 4. If I have 4 inches of fiberglass, I don't have thermal conductivity, but I know that this is 16. There you go. Okay, so now the thermal resistance of this section through the fiberglass is 31, and the thermal resistance through the rafters is 20. And then I have the thermal transmittance, the U value here. Okay. I'm speeding up things because we have seen that before, and I'm not explaining this too much because we are using the same table, and we're using the same Excel file with the same thermal resistance, the same U value. If you don't understand, or you want me to slow down, or if you want me to repeat anything, just let me know. Do you have any questions so far? Just say yes or no.
No.
Okay, thank you.
Not really.
Okay, if you have any questions, do not hesitate to interrupt me or write a chat or whatever, and I will repeat, if it's necessary, I will repeat everything again. Okay, what's next? If you look at the lesson today, that one. Okay, we have talked about the details, and now we have talked about materials of floor. So the last slide is this one. This can be the roof, or it can be the floor, the same floor or roof. We're just working with different materials. So we have It can be a wall as well, because in walls we do have studs. We have a structural element and we have thermal insulation in the middle. Okay, so we can have exactly the same issue. We can have the two different materials in walls. Okay, so when we analyze a part of the building envelope, walls, roofs, or floors, and we find that there are different materials, then we need to calculate the U value of this material, and then we have to calculate the U value of this section, two different materials. And then I remember that someone asked me, when we want to calculate the thermal loads, what do we do if we have two sections? We have rafters and we have fiberglass or thermal insulation. Does it matter? And I told you, yeah, it matters. And well, today we're going to explain the procedure or method that ASHRAE is using. So we are going to explain that first, because ASHRAE is telling us to use that method. And if ASHRAE says something, ASHRAE's wishes is our commands. So we have to do that. But on the other hand, it's easier. So I'm even if ASHRAE didn't say that, I would use that method because it's easier. So I'm going to explain the method, and then we will see how or why it is easier. Okay, so now I have to change. Okay, do you see a different screen now?
Yes.
Yes.
Okay. Perfect. Okay, so I'm going to explain this because I think I need to draw this by hand instead of having the picture there in PowerPoint, because I think it's clear. First, we're going to analyze this. We're going to analyze, it can be a roof or a floor. So there will be rafters. Okay, so those are wood rafters, softwood. Okay, and now we have a thermal insulation between these two rafters. So this is the hatch of thermal insulation. Okay, then we have boards, and well, we were using this this board here, and that was the polyisocyanate or whatever. Okay, so we need to protect the thermal insulation and the wood structure from the water. And then above this, we had another OSB board. Okay, this is the OSB board. Then we had this concrete layer. Concrete. And finally, we had the hardwood flooring. Or tiles, I don't know, we had the flooring material. Okay. Now we need to include more details. This is the sketch, but now we have to give more details. Usually, when we have structural elements, it's a good thing using axes. Okay, so just in the middle of the structural element. So the structural element here is the wood rafter. So just in the middle, we have axis, structural axis. And then we can take measurements between two axes. So the distance between two rafters, I think we agreed that it was 16 inches. Okay, this is what we agreed. But we do have other elements, so we need to work with names. Okay, so we have to write down names or the materials that we are using here. So this material is the polyisocyanates. Great. And it was 3/4 of an inch. Then this material is the soft wood rafter. And it is 4 inches. Then this material is the OSB board, and it was a 1/2 inch. This material is the concrete and it was 2 inches. And finally, we have the hardwood flooring. And that was 1 inch. Okay, so that's a good way to define a detail. Okay, so here we have a lot of information. First, we have different materials with different hatches. And here we have the name and we have the thickness of different materials. Second, we have this relevant information about the distance between two axes. We can have one more. We can add this because the width of this is 2 inches and the width of this is 14 inches. Okay, so I think this is all we need to work with this and to explain what I'm going to explain now. Well, finally, there's a U value through the rafters, and there's a U value through the thermal insulation. We have already calculated it. Okay, so now what we are going to explain is the concept of the U average. U average equals, first, we have the U value of the rafter times the width, or yeah, let's say A, this dimension of the rafter, plus the U value of the thermal insulation times the area of thermal insulation divided by dimension of rafters plus dimension of thermal insulation. Okay. In this case, or in the example that we are working with, the area of section 1, it was 0.048 times what is the width of a rafter? It was 2 inches, plus the U value through the thermal, through the thermal insulation, it was 0.03 times the width of this element, which was 14, and this is divided by 2 plus 14. Okay, so this is the concept of U average. And why is it important? Well, because by doing this, I don't have to calculate the total area of rafters, the total area of thermal insulation, and I can just okay, so if I have to calculate the thermal load, okay, if I have to calculate the thermal load is the U value of the rafter times the area of the rafter times indoor temperature minus outdoor temperature. It can be plus the U value of thermal insulation times the area of the thermal insulation times indoor minus outdoor temperature. Okay, but here I need to measure this and I need to measure that. And it's not just measuring the proportion, because I have 2 inches and 14 inches. That's fine. But what if I have 132 rafters? And so it's crazy. So if I know the concept of the U average, so I can calculate the same thermal load, and it will be the U average times the total either floor or roof area times indoor minus outdoor temperature. Okay, so this is easier because I don't have to measure all the rafters, all the spaces between rafters. I just have to measure the floor area. So width times length, and that's it. And the U average, yeah, I have to make one more I have to make one more formula, that one, but that's a piece of cake. Okay, so this is what I mean with the U average, and it's something very useful. So I will stop sharing this. And I'll start sharing that. Okay, so that's the idea. I have the U average, and I can do this with the Excel file. Okay, so on the Excel file, I have prepared these two cells here. Okay, so I can say that this is the floor and this is the U average value. And what is the U average value? Okay, so I need a formula, and this formula is going to be more complicated than the formula that we were using, which is something divided by something or something times something. Here we have to use brackets because we have to work with that formula. So I can type here equals and two brackets. So the first one is the U value of the rafters, so that cell, times the thickness or the width of the rafter, 2, plus two more brackets. So this is the U value of the fiberglass section, that cell, times the width of this fiberglass section. That was 14. And now I have to divide this by 2 plus 14. So I need two more brackets here. So I need a bracket at the beginning, another bracket at the end. Then I have to divide this, two more brackets, and this is 2 plus 14. I click OK, and this is the U average. As you can see, the U average is something that has to be in the middle. So if this is 0.04 and this is 0.03, this has to be in the middle. So it's 0.033. And it's closer to the value with more width. In this case, the width of the fiberglass section, it's more than the width of the rafter. This is 14 and this is 2. So this value, it's closer to 0.031. This is 0.033, and this is 0.047. So this value is closer to this one because the relative width between the rafter and the other one, so this is bigger. So that value is closer to that one. Do you do you want me to do it again? Do you know how to do it? The problem with brackets here is that, yeah, I think I can explain this. Okay, so we are calculating the U average. So let's open it. File. So the U average equals, and I'm going to write down the brackets here. So this is U1 times A1 bracket plus U2 times A2 bracket, and then I have to divide this by A1 plus A2. If I translate this to the Excel file, so I have to type equals bracket U1 times, which is this, A1 plus U2 times A2. We need another bracket here, divided by bracket A1 plus A2. Okay, so this is the Excel formula. So this is how Excel works. And you have to be careful with brackets, because if you miss one of the brackets, everything will be a mess. Okay? So that's why the first time it's good using a calculator, so you can use this value for the calculator, and if out of the Excel formula you have the same value, so that means that it's correct. Okay, but if you want to work with Excel, you need to know the Excel language. So the Excel language is that between brackets you have this. Okay, if you want to add up something, you need two more brackets. And if you need to divide this, you need two more brackets here. So it's So that's why when we were working with that formula, okay, if I type here, I see all, well, I see all these brackets here. There you go. Okay, so this is one cell. This is U1 times A1, U2 times A2 divided by A1 plus A2. This is the Excel formula, which is the same as this one. Any questions about the Excel file? So the Excel, as you can see, it's getting more and more complicated. We started with this, with the wall, and now we have walls, floors, or roofs, but two different sections for roofs. We have floors with two different sections for floors, and every time we have like this, imagine that we have section 1 and section 2, we have to calculate the U average. Okay, so somewhere here, you have to calculate the U average. If this is another, okay, this is a roof, so I can combine and type here roof. And then the U average, it's always equals two brackets. The first operation, it's this one times 2 plus that one times 14, two more brackets, this one, that one, divided by 2 plus 14. Okay, so this is 0.06, that is closer to 0.05 than 0.013. Okay, so because again, this is 14 and this is 2. Okay, so when we are studying a detail with two different sections, with rafters and thermal insulation, make sure that you always end up calculating the U average. If we know the width of that material and the width of the other material, then we can calculate the U average. Is it clear?
I think so.
Yeah, it's
okay.
pretty.
I hope. Anyway, I'll find out if it's clear or not, because now you have to work on your own. Now I've been working for 4 hours today. I'm exhausted. But now, from now until next lesson on Monday, I have prepared another beautiful assignment that you have to work with. So at the end of this lesson, you have the assignment. By the way, that would be part of the midterm assignment. Okay, so the midterm assignment, it will be made of different classworks or different assignments that we're going to make from now until the end of a couple of weeks. Okay, so in a couple of weeks or 3 weeks maximum, we will be having the midterm exam, and you will be giving your midterm presentation. So the midterm presentation or the midterm assignment, it will be, we will analyze this building, okay, this beautiful building that I have made up this morning. So we are going to analyze this building. It's well, it's very simple. It's a block, and but this is different. So that will be 20 plus x. That will be 20 plus y. And that will be 30 plus x. Okay, I'm doing this because I want you to have different values. Okay, so I don't want the same value, and that's why dimensions will be different, and dimensions of the building will be different depending on your student ID. Okay, so here you have to type your ID. So the last two figures in this case are, for example, 3 and 4. So X is the last figure of your ID. So in this case, it's 4. And Y is the second last figure of your ID. In this case, is 3. Okay, so if you do this, that width will be 20 plus 4, 24. This would be 20 plus y, 20 plus 3, and the height will be 30 plus 4. Okay, so unless you have the same two figures on your student ID, this is very unlikely. You will end up having different numbers, different figures, and different thermal loads. So this is what I want. So if I see that both of you have the same values and you have different IDs, that means that you have copied. Okay, so it's not that I don't trust you. I always trust people, but just in case, I don't want the same figure, the same value at the end, because it should be different because you have different IDs. So the areas will be different, and the total thermal load would be different. Okay, so this is first, and I will use this method for assignments, classwork, exams, especially in the exam, the midterm and the final exam. It will be online for sure. You have everything available, so it will be an open book, an open laptop, an open internet, so you can use whatever you feel like. The only thing you can't do is to share your exam with other students. And to make sure that you don't share your exam with other students is that your figures, your final numbers should be different. Okay, so you cannot have the same answer. Two of you with different IDs cannot have the same answer on midterm or final or assignments or exams or assignments. And I will use this thing with that some of the figures will depend on your ID. And it's, well, it's possible that you have the same last figure for your ID, but having two last figures the same, and if things get more complicated, so having 3 figures of your ID the same as other students, it's impossible. Okay, so that's why I'm doing this. Anyway, first you have to set your dimension. So the first thing you have to do is to type your ID here and to substitute this. If it's 24, you have to type here 24, 25, or 37, whatever. Then we have to analyze those walls. And the walls and roofs, we're not analyzing floors yet because we will have a basement, and for basement there's something different. I will explain that on Monday. But for walls and roofs, you should know what to do. So you have to analyze this. We have a 4-brick layer. We have air cavities here. Okay, I haven't explained how to calculate the thermal resistance of air cavities, so I'm giving you this thermal resistance. Okay, so we have air cavities. So when we have air cavities, the thermal resistance would be 1.5. Okay, so you have to include this. There is no table to find this thermal resistance, but you have to type 1.5. Okay, then you have 10 inches of fiberglass, another air cavity here, so it's again 1.5, and then ½ inch of gypsum board. Here we have in the roof asphalt shingles, another ventilated air cavity, EPS. We have 2 options here, 2 sections, the fiberglass and the rafters. So for the roof, you need to calculate the U average between fiberglass and rafters. So you have to do what we have done today, another cavity and gypsum board. Okay, so we have the wall and the roof. And here we have data of the building. So the location is Hartford, Connecticut. Now it's not relevant, but location will matter in other exercises of this assignment. The indoor temperature is 72, the outdoor temperature is 20. So we are going to use these two indoor and outdoor temperatures. What about the windows? So as you can see here, we have the south and the west elevations. There are 9 windows here, 8 windows and a door on the west elevation. So for the south elevation, the size of windows, it's 6 by 4 feet. We have 9 units. For the west elevation, we have 8 units. The window size is the same, 6 by 4. But there's a door here, and the door is 10 by 4. Here we have the U value of windows, 0.2, and the U value of the door, 0.3. And north and east facades do not have any windows. Okay, so I haven't shown those facades because they are blind. We have a wall for sure. It's the same wall. It's that wall, but we don't have any windows on north and east facades. Okay, so this is the first analysis of this building. So what do we need? Now you have to submit a PowerPoint file. It's not just the Excel file. You have to submit a PowerPoint. And we need a cover page, something nice. But the most important thing is that your name and your student ID has to be on that cover page. I won't grade any assignment without names. Okay, so if you submit a nameless assignment, you won't have any grade. So make sure that you have name, and you need the ID because I need to check whether those dimensions are correct or not, depending on your ID. A paragraph describing the assignment. Yes, so architects, we need to do a lot of things. We have to draw, we have to sketch, we have to use CAD, we have to make calculations, we have to speak, and we have to write. Because in our professional world work, there will be calculations, there will be drawings. We have to speak to persuade our clients that we are the best architects in the world, or at least in New England. And then we have to write down things because there are written documents that we need to prepare. Okay, so this is our first approach to a professional report. So we need to describe what we are doing. And what is this? Okay, we have to write it down. First, we calculate the thermal resistance of this wall. The wall is made of this, and that. The roof is made of whatever. And then we calculate the thermal resistance with this formula. So you have to write a paragraph or one of the first slide. You have to describe what you have done. And you say, why? If I have done it, and you have the results, you have the calculations, you have the formulas, you have the sketches. We need to read what you have done. And it's not that I'm mean and I'm making you work more. No, it's because in professional, we need to submit drawings, calculations, and we need to submit a report, a written report. So this is something that we have to do as architects. Then calculations and tables. Well, you have to prepare slides and you have to calculate everything that we have been calculating, R values and U values of walls, R values and U values of roofs. You have to calculate the U average of the roof here because we have rafters and thermal insulation. And then we need thermal loads through walls, roofs, and windows and door. There's a door. And finally, you have to sketch details with description of materials and dimensions. You can do it by hand, the same thing I did here on my screen. You can sketch your details, or you can sketch on a paper and then take a picture and then insert, copy and paste your picture there. Or you can use PowerPoint, or you can use oil painting, I don't mind. But I need a sketch, and the sketch has to include all this relevant information. the material and the thickness of materials, okay? And that's it. But now you have to submit a PowerPoint file. It's not the Excel file. You need to submit a report. So you can use the Excel file. You can copy this Excel file on the PowerPoint. And this can be you type here. Okay, so this can be a page or a slide of your report. Okay, so if you're analyzing the roof, this is it. Okay, and if we need to calculate the U average, that would be the U average. So that could be a slide or a page of your final report. We need a table, we need a sketch with materials and thickness, and if you need to calculate the U average, the U average. So I think it's good having a slide for each option that you are defining. You can have a slide for the wall, another slide for the roof, and other slides for doors and windows can be on the same slide, I think, because you don't need two of them. And it would be good if you start describing this with your own dimensions. Okay, so that would be the first, well, the first slide is the cover page. The second slide should include this, the building. So you can copy and paste that building, but with your numbers here, and you can write a paragraph on that building. So that building is placed in Hartford, Connecticut. The indoor temperature of the building is whatever. The outdoor temperature of the building is whatever. The wall is made of. So here you have all this information, but you need a narrative. I know it doesn't make any sense. Why do I need a narrative if I have all data here? Because lawyers don't know anything about building science, but they know a lot of narrative. And in the unlikely event that your clients are not happy with your job or your work, and you end up being sued, there will be lawyers, and all this information has to be written so that a lawyer can understand, because they don't understand drawings, they don't understand tables, they understand paragraphs. So we need this, we need a paragraph describing what we have done.